we've already integrated with the natural log, all right, but we're going to look some more in-depth at that now that we've gone through U substitution and, kind of incorporate the U substitution in with this natural log stuff. Okay, that's what our kind of goal is here. So, let's see. So remember, right, that the integral of 1 over x dx is equal to what? Natural log of the absolute value of x plus c. Okay? Or, in a more general sense, for U substitution, if we have 1 over u, or I'm going to put like du over u, something like that. Sometimes, right, the du is just multiplied up into the numerator like that. It's still the same thing as the integral of 1 over u du, right? And what would that integral be?
ln of the absolute value of u.
Natural log of the absolute value of u plus c, right?
Was that kind of thing on the quiz? Because one of the problems I got, like the ln of the absolute value of something.
Yeah, it was like number 6.
It had like a thing. It had like a natural log over x.
We've done natural logs before. I can't remember exactly if it's been on the quiz or not. And plus, Maya still has to finish the quiz, so I'm going to hold off on saying too much about it. Right. So, all right, let's evaluate some integrals here just for some practice. So, for example, the integral of 2 over x dx. All right, this is something that we could do prior to U substitution, right? We don't need a U substitution here. So, let's go to... so James, how will we integrate this here? I mean, you can, or so you said you're going to pull the 2 out front. Okay, I like that. Of the absolute value of x, yeah, plus c. That's great. Which, using our logarithm rules, what can I do with this 2?
Put it in
I can bring it back up into the logarithm as the exponent of the x, like so. And now with it written this way, do I need those absolute value symbols anymore? Why not? X squared, yeah, will always be positive, right? I mean, granted, we could put an I in there, but again, in calculus we keep it real, so we don't work with imaginary numbers, so we don't have to worry about plugging it in an I. And so, yeah, really, this would only need to be then natural log of x squared plus c. Now, you might wonder to yourself, Mr. Wimar, why would I ever do that? Why would I ever take this answer and then put the 2 back up in the exponent like that and stop, get to there? I'd be done here. Why do I need to do more work? Well, if it were a multiple choice question, right, and I give you this, and you go look at them, and you get to this answer, and you look at the multiple choice, and none of the multiple choice match this answer, you need to be able to say, oh, wait a minute, I can still pull that 2 up into the exponent here, and then it would just be natural log of x squared plus c. Yeah.
They had like a negative under the square root. They have to keep it real.
Nice. What is this for algebra 2 or something like that?
Yeah.
Okay, gotcha. They might not keep it real there, though. They might keep it imaginary sometimes. I don't know.
Yeah, she didn't know how to do imaginary, so she just had an error in her.
Oh, okay, gotcha. Keep it real. That's right. It's okay. I steal math jokes from my old math teachers too. So.
Now you're an old math teacher.
Now I'm an old math teacher. The circle is complete. Okay. So, 1 over 4x minus 1, that quantity dx. So let's go to Joey.
Oh, man.
How will we go about doing this one?
Like the outline of 4x minus 1.
Okay, so natural log of the absolute value of 4x minus 1 plus c. Okay? Question?
Oh, not really a question.
Comment. Okay, so comment.
Oh, I was going to say, wouldn't you put the 1 on the outside of the natural log?
On the outside, like a 1 times natural log?
No, like, be like natural log of 4x minus 1 on the outside. Like,
natural log of 4x and then a minus 1 on the outside?
Yeah.
Well, but it's the entire quantity here that's in the denominator, so it's the entire denominator quantity here. Now, remember guys, one nice thing about integrals and derivatives and stuff like that is like, if you integrate something, we should be able to take the derivative of that thing, and it should give us our integrand, what we integrated to get it. So if I take the derivative of the natural log of the absolute value of 4x minus 1, that becomes 1 over 4x minus 1 times what? 4. We only have 1 over 4x minus 1, not 4 over 4x minus 1 here. So it's not quite a straight-up natural logarithm here. What do we need to use? It's a U substitution. We have to use a U substitution because this is not in the appropriate format. The only thing that yields a natural log is if you get 1 over x or 1 over u, and you're integrating those. If you integrate anything else, okay, here we pulled the 2 out front and made it 1 over x. Here, this is not just 1 over x. There's other stuff with it, so we really need to use a u substitution here. So let u equal 4x minus 1. All right, and so then, Joey, what is du going to be? 4 dx. All right, we don't have 4 dx. I have a 1 dx, so I need to manipulate this dx to get it just by itself. So divide both sides by 4, we get 1/4 du equals dx. Okay, and so now it becomes the integral of, I'm going to put the 1/4 out front, 1/4 over 1 over u du, or 1/4 times the integral of 1 over u du, which then equals 1/4 natural log of the absolute value of u plus c, which then we sub in the 4x minus 1. Okay. Now, Brandon, I heard you say 1/4 off the bat without doing a U substitution, and that's fine. Okay, if you feel comfortable enough to kind of just like see the correction you kind of need to make in order for it to work, feel free to do that. But if that's like, if you get kind of confused, you're like, oh, I'm not sure if this is right or uncertain, then just go for the U substitution. But yeah, in some cases, yeah, you can just kind of see what you need to correct there.
So, on the multiple choice, it could be ln of 4x minus 1 to the 1/4?
Could be, yes. Could be, yes. I think, again, 4x minus 1 to the 1/4. I think this one here, maybe, I don't know, it's just because when you bring the 2 up, you can now drop the absolute value, so it's like different enough where students could be like really thrown off by it, which is why they might, use that kind of thing. That's why. Not that their goal is to trip you up, but just to make sure that you know what you're doing. Anyway. Okay. X plus 1 over x squared plus 2x dx. Okay, let's go to Connor. Okay, so how do you want to go about tackling this one here, Connor?
Well, integrate your sub.
Okay, let u equal what?
X squared plus 2x.
Okay, so then du is 2x plus 2 dx. Okay, do we have 2x plus 2 dx? We do not. We have
Divide by 2.
x plus 1. Oh, right. If I divide both, so I'll factor 2 out here just to kind of, yeah, I know what you're saying, and you're right, absolutely divided by 2. I just want to make it a little bit more obvious in case people aren't really sure why you did that. If you factor a 2 out here, we're left with an x plus 1 dx, which is what we have, but we need to do some of this too, so we're going to pull that 1/2, pull it over, make it a 1/2. Right, divide both sides by 2, so it makes it 1/2. du equals x plus 1 dx. And so then this becomes, 1/2 goes out front, integral 1 over u du. Well, that's pretty nice. Okay. And so we get 1/2 natural log of the absolute value of x squared plus 2x plus c. Kind of skipped the u part, but I feel like, well, maybe I'll put it right here. Okay, there it is. There it is. Good.
I have a question.
Yes, question.
So if we wanted to put that 1/2 onto the x squared plus 2x, would we still have to keep the absolute values, or is it implied because we're in calculus that it would be all real numbers, therefore not worry about
So if you brought the 1/2 up and it was a square root,
keep absolute value.
I guess not. No, you wouldn't have to. Huh? Same thing for the 1/4 either. I would imagine.
Yeah.
Same idea. Yeah. Okay. 1 over t times the natural log of t. Okay, so I'll let people kind of think about this one for just a second or two here, so you can say, okay, what? So it's probably going to be a U substitution, right, because that's what we've been doing. T times the ln(t). So, Emma, any ideas here? Birthday girl.
Would you just,
Let U equal ln(t) is what you're saying? Okay, so then du is what? 1 over t dt. Do we have 1 over t dt? Yeah, we do, right there, right? There's the 1 over t, there's the dt, and so, let's see here. So, this ends up being the integral of what then?
integral of 1 over t times u.
Okay, we have 1 over t dt, that's the du, so that's just taken up by the du, and we have 1 over the ln t, that's our u, so it's 1 over u du actually is what it is. You see that okay? Okay?
I usually like plug it in just so I can see.
Oh, I see what you're saying, and then you do the du later?
Yeah.
Gotcha, that's fine, absolutely do that, yeah, that's great. That's fine. All right, Emma, what's the integral of 1 over u du?
Can you change it so u is negative?
If you want to, sure.
So then u is
You're right, so it gets u to the 0, and then you divide by 0. Be careful, though. What's the integral of 1 over u du? We just talked about it at the top of the paper.
the ln of u.
Yes! Great job. That's exactly right. It's the natural log of the absolute value of u plus c. Okay? And again, the good news is, right, so yes, it's very tempting when you see 1 over u to then maybe rewrite that as u to the negative 1. That's a good thing to think about because students tend to get that mixed up. Sometimes I see students, they see something like 1 over u squared and they try to do a natural log. If it's 1 over u squared, that's when you want to rewrite it as u to the negative 2 and then use the power rule. And then sometimes I see students do it this way, where they see 1 over u, and they rewrite that as u to the negative 1, and they want to apply that power rule, but then you kind of run into an issue, like, wait a minute, it's u to the 0? That doesn't make sense, right? And you're right, it doesn't, because it's supposed to be natural log. So you can mix it up both ways, so be on your toes about that, right? And so then our final substitution back in there, it's going to be the natural log of the absolute value of the natural log of t, okay, plus c.
Is that all right? Have a natural log of a natural log?
Yeah, sure. Yeah. Yeah. Is it funny? You. Okay.
That's what I'm looking at right now.
There it is. Okay. ln of the ln of x. Interesting. Okay. Oh, because right, that makes sense because the yeah. ln x. Delete that. Delete that. Delete that.
Can you show it on the overview?
Yeah, sure.
Interesting.
It's like it's got a. I guess I'm assuming that's a pointy. That's pointy probably, which means that it's not differentiable there, right?
That's pointy? It doesn't really connect.
It looks like it's, well, that's a graphing calculator error. I'd be willing to bet. There you go. It gets the point there when I draw it for more zoomed out. So yeah, it'd be not differentiable there. Which makes sense because it'd be over 0. Anyway, okay, let's keep going. Let's see, I got a few more to look at. We're going to do some definite integrals now. So we're going to evaluate some definite integrals too. Okay, so the integral from 0 to 1 of e to the x over 1 plus e to the x dx. Okay.
Mr. Wood,
Yep.
I typed in the last function and it froze my calculator.
Nice. Did you hit the enter button or something like that? Because that sometimes pauses the graphing too.
Oh, yeah.
Yep, okay, I got you. See, I can read your calculator from here. All right, Brandon, what do you say here?
I say this one. Hard problem.
Okay, well, give it a shot.
Sub of 1 plus e.
Let u equal 1 plus e to the x. Okay. That means the du is what? E to the x dx. Okay, that's good, right? So far, so good. That's what we want. Because we have e to the x dx here. So then I'm going to rewrite my integral here, and what will my new integral be? Okay, so yeah, du over u or 1 over u, that's fine. And integral from 0 to 1? Why not 0 to 1? That's what my limits were right here.
Oh, never mind. Well, yeah. Do one.
I do want 0 to 1?
Wait. No, you don't, because it's in u, in terms of u.
Right, there we go. Okay, so it's a definite integral, but 0 to 1 are limits of integration in terms of what variable? X. We need to if we're going to rewrite our limits, we need to then translate these into u limits of integration. Alternatively, you can leave it like this indefinite integral, evaluate it as you see it, plug back in for the x, and then evaluate from 0 to 1 once it's back in terms of x. So you have two options there. I like to adjust the limits of integration because, you know, we have it here, so let's do that. So, all right, 0 to integrate, to change that, it's going to be e to the 0, which is 1 plus 1 is 2. And then my other upper limit of integration is going to be, let's see, if I plug in 1, it's e to the 1, so it's e, so it's going to be the limit of 1 plus e. Okay, which is a number. It's a funky number, but it's a number. Okay? So now, integrate that, right, you said it was the natural log of the absolute value of u, evaluated from 2 to 1 plus e. Okay, and so we just plug that in. So it's the natural log of the absolute value of 1 plus e minus the natural log of the absolute value of 2, which is then just really ln of 1 plus, just like parentheses. Okay, there it is. And we could do one more step here. When you have subtraction between two natural logs, what does that become? Yeah, division. So you could say natural log of 1 plus e all over 2 like that, using those natural log properties.
Will that not just give you 1?
Sorry?
Should that not just give you 1? Because when I didn't solve for the limit in terms of u. I solved it through normally and then plugged in my x values for u and then solved it that way.
I don't think it's going to be, I don't think that equals 1.
I don't think that's right.
Okay.
ln of, yeah, because I got ln of
You
e
didn't
to the x plus 1.
plug in the u, you just put in what the limit was in the absolute value. So it should be 1 plus e to the 1 plus
No, I evaluated my integral here using my u limits of integration.
Yeah.
Oh, so you did it, okay.
Right, so alternatively, we could have written this in terms of, and I'll show you guys this here real quick, we could have just done du over u, not writing our new limits of integration,
Yeah,
making it
I
natural log of the absolute value of u plus c, and now we'll change it back in terms of u, in terms of x, so it's 1 plus e to the x plus c, evaluated now from 0 to 1 because it's back in terms of x. And we end up with natural log of 1 plus e to the 1, which is just 1 plus e, minus natural log of 1 plus e to the 0, which is then going to be 2, because e to the 0 is 1. And so it does end up being the same thing then.
Why did you take away the
Here, because 1 plus e will already be positive and 2 will already be positive, so you don't need them there. And the same thing for this case too, it'll be the same thing. So, okay. Woof! Fun stuff, right? All right. This is what Emma asked for her birthday. I was going to have a party, but Emma's like, no, Mr. Witt, we're going to do calculus. Okay, Emma, you got it. You're the birthday girl. I was going to bring in a clown and everything, but she didn't want a clown.
Were you going to be the
Afraid of clowns. I was going to be the clown, yeah.
Oh!
Oh my god.
Boy!
I'm sorry, Ryan.
Oh my goodness gracious.
Okay, let's try another one. Here we go.
That was good.
Integral from 1 to e.
Might have to rewatch that on the video tonight.
Ashton Kutcher just comes out of nowhere. He's like,
It's a 4x squared.
Oh my god.
That's supposed to be an E there. I believe it's supposed to be an E, yeah.
What?
Okay, so, let's see here. Ryan, what do you say? What should we do here?
Well, I'm gonna say let U equal 4x squared plus 1.
Let U equal 4x squared plus 1. Let U equal 4x squared plus 1. So du is 8x dx. Okay.
You don't got an 8, so you gotta make it just 2x. So you gotta divide each side by 4.
Okay, so you make it 1/4
1
du equals 2x dx. Okay.
Okay.
We still have a problem though.
It's not.
This is not 2x dx, it's 1/2x dx. And this is 2x dx.
Oh, so could you do, instead of 4, could you do 6?
So we could, okay, yeah, we could still make it, we could make it 1/2, but the problem is we still don't, this x is not going to be in the denominator, this x is in the numerator, right? It's x times dx, not 1/x dx. You see something that's 1/. So yeah, we don't want to let u equal 4x squared plus 1. Johnny, did you have an idea? Or? No, you don't, I thought you had something to say, sorry. Okay. So that's not our u, nope.
Alright, well then could
I
you
think I know what we do.
start by putting, well, how does that work?
So let me say this. We could do this one before u substitution.
Bring the 2x up then.
Bring it up if you want to, just do the division. So like what Brandon was saying, we could break it up. So yeah, so this is one we could do before. This is not a u substitution actually, which I guess it's not fair for me because we're doing all these u substitutions, and I didn't tell you that was a potential option here. So that was kind of tricky. Okay, but yeah, we can break it up like this if you want.
Yeah.
Okay, or you can bring it up and then distribute the 2x. I'm gonna break it up like this. I like this more, but again, you can bring it up and distribute if you want. That's fine. So now if we simplify that, it's the integral from 1 to e of 2x plus 1/2x dx.
Split those up.
Yes, excellent. We should break up the integral. And why am I allowed to break up the integral like that? Yes, we have addition. Okay, you are allowed to break up an integral over addition and subtraction, and that's it. If you have a product, you cannot break a product up with an integral, but you can add and subtract. So, and they keep the same limits of integration, all that good stuff. All right, integral of 2x, what will that become there, Ryan?
X squared.
X squared, yeah, just x squared, because then 1/2 times the 2. I'll go ahead and just write that out, just so that way it can, be there. And then integral of 1/2x. Well, let's see here. Let's manipulate this sum. So this is the same thing as 1/2 times the integral from 1 to e of 1/x dx, right? I should probably put the plus. There needs to be a plus c in here because I integrated 2.
Wait, it's a definite integral then?
Yeah, but I'm going to put the plus c in because I haven't evaluated the definite integral just yet. So, yeah, it's kind of like, I don't know if I'm being too picky here or not, but I guess better to be too picky than not picky enough. All right, integral of 1/x is natural log of the absolute value of x. And then we can finally then evaluate that from 1 to e, the whole thing, because they both have the same limits of integration. No, 1c is sufficient because this... Oh, yeah, no, because it's all one thing, we can just evaluate the whole thing from 1 to e, because it's all being evaluated from 1 to e. That's what we plug in, right? So it's e squared plus 1/2 ln of e, that quantity minus 1 squared plus ln of 1. Remember, when you're subtracting, when you're doing your upper limit minus your lower limit, put parentheses around your upper limit and your lower limit. This minus sign distributes to the pieces there, okay? That's why it's so important. Yeah.
I don't know if you meant to do this or not, but should there be a 1/2 in front of the second ln?
Oh, thank you, yes.
Okay, I
This
just
one,
wanted to
yes.
make sure
Nope,
that-
you're good. Nope, thank you, I did miss that. Thank you. Okay, but it's super important here. Parentheses around the upper limit minus parentheses around the lower limit, okay? Now, again, if it were a free response question, we're done. But we can actually simplify this pretty nicely. Okay, what's the natural log of e?
1.
Yeah, it's 1, okay? So it's e squared plus 1/2 minus, okay, 1. What's natural log of 1? 0 times 1/2 is still 0, so it's this, which is then e squared minus 1/2. So that kind of simplified rather nicely to that. Okay. Okay, so good. All right, let's try another one here. We'll do 2 more together, and then I have 1 for you guys to try. Birthday bathroom visit. Very nice. Okay. Integral pi over 4. Oh boy, you know what that means. It's time to do trig. Good. Don't like that one. All right, Chanda, what do you say? How can we maybe do this?
Let's do it.
We can do that. Let's do some of this 9 and 7 first of all. The 9/7 there, what can we do with that? Yeah, we can pull that out front. Let's do that here real quick, just because. And then integral, and then, yeah, okay, so you want to let u equal what here? Tangent theta, okay. And so then du is secant squared. Oh, perfect. Excellent choice. Okay, d theta, don't forget the d thetas, right? And so then what does this integral rewrite to be? I pulled the 9/7 out, so what would it be then? Yeah. Something that looked real nasty there actually turned out to be not too bad. Okay. Now, do you prefer to convert your limits of integration from theta to in terms of u, or do you prefer to wait till the end and then evaluate them? Which way do you like to do it? You want to wait till the end? Okay. So then 9/7, let's see, integral of 1 over u is natural log of the absolute value of u plus c. And so then 9/7 natural log of the absolute value of tangent of theta plus c. And we're going to evaluate that from pi over 4 to pi over 3. Okay? And so we'll plug those in. 9/7 natural log of the absolute value of tangent, pi over 3, minus 9/7 times natural log of the absolute value of tangent of pi over 4. And again, it's not a bad idea to put parentheses on your upper and lower limits, even though in this case there's not really a quantity. I mean, there's not addition, subtraction, so it's not a big deal, but yeah. Okay. Tangent of pi over 3. It's a free response question, right? That's true. So we could just stop right there if it was a free response question. Let's evaluate though. What's tangent of pi over 3? I'm not gonna put Chanda on the spot there. Okay, yes, it is root 3. So absolute value of square root of 3 minus 9/7 times the natural log of the absolute value of tangent of pi over 4 is
Root 4?
It's 1. Just 1. What's the natural log of 1? 0. So that whole thing, that whole lower limit disappears. Okay? And so, and again, if you want it to be kind of like, not sneaky here, but 3, square root of 3 is 3 to the what exponent? It's 3 to the 1/2. And because that's an exponent, what can I do with that exponent? Bring it out front, and so we can also say like 9/14 natural log of 3. Okay? So lots of options there. All right, one more. I'm going to have you guys try one. Uno mas. Uno mas. And you guys try one here. Okay, and then we might stop for the day from there because I think I've just got inverse trig at that point. Okay. Integral 1 to 2 of 3n over the square root of 5 minus n squared dn. That is an n squared, yes.
Oh, okay, thanks for putting that. Oh my god.
All right. Christian, what do you say here? What are we going to do?
I'm gonna try use stuff.
Okay, let u equal, what do you say here?
I want to do 5 minus n squared, but I don't know.
Let's try it. 5 minus n squared. So then du is what?
Negative 2n.
Negative 2n
D.
dn. Let's see here. So I'm going to pull that 3 out front, so that way we don't have to worry about the coefficient there. We'll make it just n over the square root of 5 minus n squared dn. And so we need then just n dn for mine right here, right? So we're going to divide that negative 2 over.
Right.
And so then this really becomes negative 3 halves integral. I'm going to leave the limits right now because we're going to turn into u. So we have n dn. Yeah, it's good. So it's 1 over the, what's my denominator?
Square root of u.
Square root of u, which is not, it's just u to the 1/2 then, right? So 1 over u to the 1/2 du. Right, like that?
Okay, Ryan.
Can you change that to 1 over u, or just u squared? Does that work?
Not u squared.
Oh, it would just be u to the negative 1.
There you go.
Yeah, okay.
It was Emma.
Okay, Mr. Wood.
Thank you.
Of course it was Emma.
Thank you, Mr.
I know
Wood.
who it is.
Mm.
I do feel confident.
So there's our limits of integration, which means this is natural log?
No.
No, it is not natural log, okay? So another thing we have to be very careful of, right? Just because you see, and I mentioned this earlier, just because you see 1 over something does not mean it's natural log. You only have natural log when it's 1 over u to the 1, and that's it, or 1 over x to the 1, and that's it. Any other power, you're going to use the power rule, okay? Any other power, use the power rule. So, what does this integrate to be then, Christian? U to the negative 1/2 becomes u to the what?
Oh my God.
U to the 1/2.
1/2, and then we multiply by 1 over 1/2, which is really just 2.
Yeah.
So the 2 and the negative 3/2 cancel there, and we're left with negative 3u to the 1/2 plus c, and evaluate it from, oh, nope, not yet. I've got to plug back in. 5 minus n squared
So, just 4.
to the 1/2 plus c, and evaluate that from 1 to 2.
Oh, you changed it.
Yeah, you don't have to. If you did, that's fine. I mean, I didn't hear you say about changing the limits of integration, so I just figured you were going to wait till the end. But that's fine. Do it that way too. And now we finally plug in. So negative 3, 5 minus, let's see here, 2 squared to the 1/2 minus, and again, we use quantities here. I use parentheses, I mean, negative 3, 5 minus 1 squared to the 1/2. And there's your final answer if it's free response. But of course, we're going to simplify this because we can.
Just because.
So let's see here. 2 squared is 4. 5 minus 4 is 1. 1 to the 1/2. 1 times negative 3, negative 3. God bless you. 1 squared is 1. 5 minus 1 is 4. 4 to the 1/2 is?
2.
2 times negative 3 is negative 6. So minus
Plus.
negative 6.
So
So
you
plus
3.
positive 6, which is 3.
Nicely done.
Aww. Little 3 right there. Okay? Alright, here's one for you guys to try.
nice.
Finally. I know you guys have been waiting. When do we get our shot? Find the area
Okay, so agreed.
bounded by the graph of y equals x over x squared plus 1, the x-axis, and the lines x equals 0 and x equals 3.
So from 0 to 3.
Okay. So go ahead, give that a shot.
Question, yes. Didn't we want to use like a test review or something?
I think so, yeah. So what do we have that helps us find the area under a curve? Integration, that's area of the curve, isn't it? That's one of the concepts that we, so.
So then how do you just, the limits of integration are 0 to 3?
Because x equals 0, that's a vertical line, x equals 0, and the other line's a vertical line, x equals 3.
What is it, the x-axis, like, what does that mean?
So whenever you integrate, right, we're finding the area under the curve. But if I just draw a random curve and I just say the area underneath that, the area underneath that curve goes on forever.
Yeah.
It's not really the area under the curve, it's the area between the curve and the x-axis. That's what we're finding. So that's why the x-axis is one of the boundaries.
So will that matter when we go solve for this?
I mean, when you integrate, your boundary is
Okay.
the x-axis.
Do you want a number or just in terms of?
Yeah, I guess that's fine, yeah. You can just give me a number, I guess. That's fine. Or, again, yeah.
Would you get? Move it up.
Like this? You move it up, different person. You're not talking to me.
Could you move it up and distribute it?
That's what I do.
You could. Mm-hmm.
You can't take the national log rate.
But how would you distribute that, though? Because the entire
Oh, no, you
quantity
can't.
x squared plus 1 is being raised to the negative 1.
Oh, then never mind.
Like, yeah. If it was flipped, if it was x squared plus 1 over x over x, then you could do it. It would be helpful. But otherwise, it would take it. Otherwise, nah.
It doesn't work, does it not?
What doesn't work?
Well, because this x is on the denominator, isn't it? Yeah, what I'm saying is like, I know, yeah, I know. I was being stupid for a second.
You didn't? Don't you do that?
Called me.
Oh, wow.
Like the thing we've been doing? Basically, yeah. I mean, the idea, so you understand what I'm actually we're bounded by the graph of that. The area of the curve, you know that's an integral, right? So you're entering
Sound like
that.
it's making noodles. Oh, it's just too big.
Exactly, because what is the line x equals 0? It's a
Ryan, why do you
vertical,
have this?
Right, and then x equals 3 is another vertical line. So when
did
you integrate, you kind of integrate,
I moved
vertical
that.
accumulation and left to right. So, yeah, what's your bound?
It was.
So that'd be like, if you were to be yeah, there.
I'll
go left.
1.15.
Yeah, great job. You do the decimal for it, so I can, because I can check the decimal, get the decimal. Nate, you doing okay? Oh, it did, okay, that's fine, I can take a look. Yeah, so, what's the derivative of x squared plus 1? So it's 2x.
Do you have it in one?
Yeah. Yep, very good. Okay, all right. Yeah, it should be, yep, that's, oh, it should be 1/2 the ln.
1/2?
Oh,
Yes,
I didn't
because-
bring it down. Yeah, don't forget that, yep, exactly, it's very easy to do that, when you pull that out front like that, it's easy to forget about it.
Okay, so a lot of good stuff there. Let's go to Maya. Maya, how'd you set this up? Well, I mean, like, what's your like even your initial like work here? Well, how'd you start this? Integral from 0 to 3. Okay, yeah, of x over. Very good. Okay, that's right. Dx. Excellent. And so you said then a u substitution, right? Let u equal what? Okay, and so then du is. Very good, yeah, very good, yeah, 2x dx. And so we don't have 2x dx, we just have x dx, so we'll make this 1/2 du equals x dx. And so this becomes then 1/2 the integral of 1 over u du. du over u? That's right, because I mean I can multiply the du up into there, and it'll be the same thing. Did you change your limits of integration here?
Yeah.
Okay, so what did you get for your new limits of integration? So you said this number right here should be a 0 and this should be 3/10?
Well, don't you plug in like 0 to the, and then 3?
So you plug 0 in for the x. This is an x limit integration, so 0 squared, 0, and plus 1, so it should be 1. Oh, no, okay. You see what I'm saying, though, now? Okay, so then 3 squared, 9, plus 1, 10. Okay, and so we end up then with 1/2, and then this is the natural log of u, absolute value of u, and we're going to evaluate that from 1 to 10. Don't forget to distribute that 1/2. Okay. But it still worked out, though?
Yeah.
Interesting.
Yeah,
So-
we use the same limit, so then when I put in ln of, x squared plus 1.
Oh, then you use 0 to 3?
Yeah.
Yeah, no, see, that's right. That's an alternative way to do this. So either you can translate the x limits of integration into terms of u, and then you can just go ahead and plug those in once you integrate the u, or once you've integrated u, you then plug back in x squared plus 1, and then use 0 to 3 again. So either way does work. There are two different ways to do it. So that's the answer, which is approximately 1.151, I believe. Okay? So there you go. All right.